All right, questions? No? Anthony? Oh, no. I was going to post it yesterday, but I didn't get to it. I'll do it this afternoon. I'm going to see a copy of last year's exam. I'll post it on Piazza. Uh-huh. Yeah.
I'm just curious, how do you do receive?
If you read out the question, maybe.
Yeah, let me see. So it's mainly, I'm not sure how you get the Roman numerals in that.
Okay. Just go ahead and write. Give me the formula then.
Okay. It's PP, and then for water, so aqua. That's the first one in brackets. And then the second one is PP and then 6 chloride ion. So no parentheses on that one.
Like that.
So I'm just confused on getting the Roman numeral part. So I looked at my solutions. But other than that, I know how to break it out.
All right. One, do you know the two common charges for platinum? 2 plus and 4 plus. And so one of the ways you could do it is just guess, If both of them were 2 plus, does that work? If both of them were 4 plus, does that work? If one's 2, the other's 4, or if one's 4, the other's 2, does that work? And so you could just try some guessing with the different combinations of plus 2 and plus 4. But this one, what I wanted you to do for this was I wanted you to look at that table, the 2, 4, 6 table. Did you look at that? And then see something in that table. And what you see in that table is that 4 coordinate platinum is plus 2, and 6 coordinate platinum is plus 4. And so basically the tetra aqua, that's 4 coordinate. And so this has got to be platinum 2, and this is 6 coordinate, and therefore it's got to be platinum 4. And that's what.
We're gonna have the chart provided on the exam, right?
No.
Okay.
No. For homework, everything's fair game because it's open book, open notes, whatever. For the exam, I'd be a little. I wouldn't.
The way the format I was going, I was just trying to figure out oxidation state numbers. I wasn't completely aware of. I was aware of this chart, but I wasn't looking at it. I just started homework now. So.
Yeah, that's fine. On the exam, I wouldn't expect you to have anything memorized, for the coordination numbers. It's just for this particular. And so this is common every semester. I get asked this one about platinum because it's hard to tell what the charges are. And so the easiest way is to look at that little chart and then see. Platinum 4 coordinate platinum is always square planar. Platinum 2. 6 coordinates always octahedral. Platinum 4.
Wait, did you say for the homework we're only doing part of it since we're doing already the section?
Yeah.
So if you don't have a homework with 1 to 6 and then 7 to 7C, do we do all of the ones you posted or just stop at 8 or something?
All the ones.
I'll do all the ones you posted?
Yeah, I split it up into part 1 and part 2.
Okay.
Part 2 is later on for the rest of the sections. Chapter.
Does the exemplar, do you have to also know how to draw the structures?
For which specifically, which structures? For example, EDTA, no.
So we have to draw the structures,
For example, 7D.
7B, tell me what that question is.
FAC. Do you want to see?
No, I just would rather just.
It starts with FAC and has a dash and then dual brackets.
That was 7B?
Yeah,
All
and
right.
it says draw plot construction.
All right. You aren't gonna have to draw structures like that.
Like this one?
Yeah. In fact, that's a mistake. I made a mistake. That was actually a part 2 homework problem, not a part 1 homework problem. And so that was isomers. You don't have to worry about isomers. When I say draw something, you know, I might ask you, for example, how are the water molecules attached to platinum? Show me. Right? Can you show me how the water molecules bond to platinum? That's what I want to see. You know, and I want to see the correct number of lone pairs. The book does something weird. You know, usually when you have a line here, that line represents 2 electrons, right? And sometimes the book will have too many electrons in there. And so I've been trying to avoid that. And so if you have platinum here, you know, and it bonds to water, the water is going to give up one of its lone pairs to make that bond. This is a Lewis acid-based reaction. And so I need to see something like this, you know. If I'm looking at how platinum bonds there, it's going to look like this. That's, you know, that's the extent. Now the isomer stuff will come much later. We'll do that. But structure as far as, you know, we were talking about this coordinate covalent bond, all this stuff.
So we would skip
Electron
that.
pair donor. Hmm?
Should we skip that question?
Yeah, skip that question.
So for tomorrow, only part 1 is due?
Only part 1 is due.
On the homework, where does part 1 stop?
On the homework assignment sheet, it tells you. Yeah, just everything in part 1. And then part 2 is at the bottom of the homework assignment. Okay, other questions? No? You know, so some of the problems are like the last problem in homework set part 1. You know, in order to answer that, you know, the easiest way to answer that is you look in the book and you see pictures and that kind of stuff, and then you can figure it out. But to sit there and try to figure it out without looking, you know, for some structures is a lot more complicated. You know. And so some of those homework problems, for sure, you have to flip in the book to find the answer. Otherwise, you probably aren't going to come up with it easily. Like this platinum, you know, this platinum charge is hard if you didn't know that other information.
For tomorrow, we have to identify which complexes with Bronsted acid and base.
Not which complex, which species. Like that, you know. You have to identify the Bronsted acid and Bronsted base for tomorrow, or complex. And let me you must be talking about Lewis, right? Not Bronsted, because in complexes it's just Lewis acids and Lewis bases, no Bronsted acids and Bronsted bases for Lewis, for complexes.
Because on the homework, there's number 33,
Mhm.
it asks for to identify which of the following acts as a Bronsted acid.
All right. That was in part 1?
Yeah.
Yeah. You know, okay. Sometimes I do this differently, the timing of things. And so one of the things happens when water bonds to platinum like this, you know, like this. How does that change, you know, the properties? Is it still like water? You know, it's aqua. It should be like water, right? But when water bonds like this, it changes. It changes something, and one of the things it changes is it changes the acidity of water. Water itself is not very acidic, right? Acids, base, pretty weak one at that. But when water is bonded to a complex, then it becomes quite acidic. The reason it becomes quite acidic is because of this. You got a platinum with a 2+. You guys You guys familiar with the inductive effect? Inductive effect? Did you hear about the inductive effect in chapter 10 and 11? I know Anthony, you must know. Utama, you must know the inductive effect pretty well. What about you other guys? I talk about the inductive effect a lot, because, but you haven't heard of it? All it is a shift in the electron cloud, a shift in electron density. And so what happens is this. Normally water, is very polar. I should have talked about this. Water is quite polar. And it's because of oxygen. Oxygen is very electronegative, 3.5, right? And the hydrogen is going to get delta pluses here. These delta pluses are big because these very big delta pluses lead to hydrogen bonding interaction. Hydrogen bonding occurs when hydrogen is bonded to oxygen, fluorine, or nitrogen, the three most electronegative elements in the periodic table. And it has to do with the three most electronegative elements pulling the electron cloud to it. And so the electron cloud is going to be pulled towards the oxygen. When aqua bonds to essential metal, that changes how the electron cloud looks in here. And what happens is, yes, oxygen is normally quite electronegative, but in this case, oxygen is going to be even more electronegative. When I see an oxygen bonded like this in a complex, then I look at that oxygen. That oxygen should have a higher electronegativity than 3.5. The reason is there are different ways we can think about this. One way I'd like to say is because when oxygen forms three bonds, it's got a positive formal charge. But remember, we don't count formal charge in the normal sense for these. And so if you have a positive oxygen versus a neutral oxygen, a positive oxygen is going to be a heck of a lot more electronegative than a neutral oxygen, right? That's one. And so if you have a positive oxygen, it's going to suck even more electron density away from the hydrogens. Sucking even more electron density is going to make these hydrogens much more positive. That changes its acidity, right? Changes its acidity. But we can't use formal charge here because we're not supposed to count it like that. And so what we say is the platinum is +2. It's electron poor. It's going to start sucking electron density away from oxygen. As platinum sucks electron density away from oxygen, oxygen in turn is going to suck even more electron density away from hydrogen. This is called the inductive effect. We show it with these arrows, like dipoles, like this. Whereas here, it just gets sucked towards oxygen and it stops. Here, the oxygen is getting electron density sucked away because platinum's 2+. And what happens is it makes the water much more acidic. So aqua ligands are quite acidic. So acidic that, I don't know if I mentioned this before, but this is all I was supposed to have mentioned this, but okay. There are two unusual species on this chart. One is the hexaaqua aluminum 3 ion. Hexaaqua aluminum 3 is a stronger acid than carbonic acid, or weaker, just slightly weaker acid than acetic acid. But, hexaaqua aluminum 3, that's just aluminum 3 ions in water. That's it. And so if you have a solution of aluminum chloride, it's quite acidic. This pH is going to be comparable to acetic acid. And so having aluminum chloride dissolved in water is like having acetic acid. And that's because of that. The other unusual species is this. This is the hexaaqua iron 3 ion. The hexaaqua iron 3 ion is very acidic. It's more acidic than hydrofluoric acid and a little less acidic than phosphoric acid. This is really acidic. And so these two unusual species in the acid chart, and these are in the acid chart that I handed out as well. And did you guys see these species in the other acid chart? And so this is why I had question number 33 on there, was because of the Bronsted acid. But it's a Bronsted acid because hydrogen, this makes it much more attractive. If I'm a base like hydroxide, I'm going to pluck this proton off here versus a proton off water. This proton is going to be much more attractive. But that doesn't have to do with the ligand, what we're talking about. Well, the main acid-base interaction we're talking about in chapter 24 is a Lewis acid-base, not the Bronsted. The Bronsted is a side thing to try to explain this Bronsted acid-base chart here because there are two unusual entries in there. That's it. I know we have the iron in our handout chart. I'm going to talk more about this in chapter 16. When we get to chapter 16, then we're going to look at that in detail. All right, other questions?
So that would be questions similar to 33 on the test.
No? Uh-huh.
When we construct the structure, is it like when we get marked off, if like we orient like the OH2 different than the H2O, or does it have to be?
It has to be OH2. If you did H2O, you know, how's it bonding? You know, I know what you mean if you wrote it like this, but if you're going to write a structure, you know, you got to write it. And so this is obviously wrong. This is wrong. Can't be like this. Can't be H2O in that sense. So this is why I wrote it backwards, because it's the oxygen that binds to it. Excuse me. Not the hydrogen. And so oftentimes we write things backwards, like you'll see, rather than writing it, well, why didn't I write it OH2 here? I didn't write it OH2 because I'm not really showing the bonding. If I'm trying to show the bonding, I better write it OH2. And then technically, this is not right. Too many electrons. That would give this one way too many electrons. And so the book does something funny with it. Uh-huh.
If you want it, if you want us to actually draw the H's bonding to the
I'd like it like this. But, you know, it's just a matter of preference. It's like when people do ethylene diamine, you know, do you want the hydrogens shown like this? Do you want the hydrogen shown like this in an expanded structure? Or do you want to do a condensed structure? Like this? And the answer is it doesn't matter. You know, both are fine. Condensed or expanded. Expanded is, you know, as long as you can do both here. Uh-huh.
Could you explain to me, 4D? It's mean chloral bis ethylene diamine polyethylene. You want us to recommend?
I
My
had
question really is between,
a mean and ethylene diamine.
yeah.
All right. In an effort to make your life simpler, I might have made it more complicated. In order to make your life simpler, I said when you order the ligands, just put them in alphabetical order according to name. The reason I said write it in alphabetical order according to name is your book is different. Your book says put it in alphabetical order according to the first element of the formula. And so according to the first element of the formula, this has two different orders. Do I do it based on hydrogen, as in the normal formula, or do I do it based on oxygen to show, you know, it's the oxygen that's binding to it? this is going to change its position. Whereas both of these are aqua, right? This is aqua doesn't change. And so since aqua doesn't change, I said, do it according to the name, not the formula. Now, what is the formula for ethylene diamine? Well, you know, you guys that know in Chem 1A, there are different ways we write this formula, right? And so if this is the structural formula, the condensed structural formula, we have the expanded structural formula, but then we also have the, you know, let's just do. Okay, so this is ethylene diamine, right? And so do we do it by the N of ethylene diamine? Or do we do it by the, because in organic chemistry, you usually write the carbons first. So if we write the carbons first, it'd be C2. And then what is, we do something like this, C2H2. And then we might do this, you know, do partial, like a hybrid, you know, NH2 or we might do it like this, C2H2N2H4. Or we might go for something like this, combine all the hydrogens, C2H, this should be 4, sorry, C2H8N2. This is usually the way you see it, right? C2. So should we do ethylene diamine according to the N of the condensed structural formula? Or should we do ethylene diamine according to the C of the conventional organic formula? Or maybe we had an H first. Maybe we wrote an H2N, CH2, CH2, NH2 to show the symmetry of this. Or should we do it according to the H of this symmetric formula? Which should we do it? And the answer is none of the above, because they don't do it according to the symbol. They do it according to the letter of the abbreviated name, and they call it E for ethylene diamine. And so this has always bugged me, because when you go out there, it depends on who writes the formula. Some people like to write the formula like this, some people like to write it like that, right? If you could get everybody to agree to write the formula the exact same way all the time, then we can use the formula. But, you know, since there's different ways to write the formula, do you call this aqua and then you call this, what's the backwards of aqua? Aqua, ka? You know, since it's backwards? No. Both of these are aqua. And so, you know what? I said, just name it according to name. And so that's why. There's another point to this. And the other point is that about 5 or 10 years ago, they switched the system. And so it used to be that neutral ligands went first. And so now they have the anion ligands go first, so that's easy. Chloro is going to go first. And therefore, we have 1 amine and 2 ethylene diamines. Which one should go next? I say amine goes next because according to the name, A comes before E in ethylene diamine. But here, they're saying, okay, you know, we're going to say everybody uses that as the formula. That's not really the formula, that's a name, an abbreviation of the name, right? And so, make a long story short, do whatever you want, but be consistent. If you use the books method, you know, go ahead, do it according to the formula. You know, and the abbreviated formulas. You know, like oxalato. Oxalato, you'll see in books, many books, oxalato is written like this. So if I had dioxalato, it would be looking like that. A lot of people don't use OX for oxalato because it's a short formula. A lot of people use EN for ethylene diamine because it's a long formula. And so oxalato is very simple. And so do you use carbon or do you use Do you use C or do you use O for that? No, you would use, according to the book, you'd use O, right? But you'd use O if somebody wrote it oxalato. You'd use C if somebody wrote it C2O4. OX instead. You see? And so I try to make your life simpler by just saying, forget the formula, just do it alphabetical according to name. And so oxalato would go O for oxalato. And so myself, I would have put amine in here because A comes before E, and then the ethylene diamines like this. The book is going to put the ethylene diamines first, and then the amine. It's fine.
Another way is better.
Otherwise, in truth, they have these committees trying to decide consistent rules for name. And so the rules have changed because they're arguing back and forth, you know, what's a better system for naming these. This is a disagreement. You're going to see a wide variety of names out there for the same thing. You know, it's like I was looking for ammonia. Did I tell you? I was looking for ammonia. I didn't tell you this? I was looking for ammonia. This is a European chemical manufacturer, and I said, wow, I can't believe they don't have ammonia. I needed some ammonia. It turns out they did have ammonia. They just didn't call it ammonia. You know what they called it? They called it, no. They called it nitrogen trihydride. So there it is, oh, nitrogen trihydride, you know. It's like the dihydrogen monoxide, you know. Just, it's foreign to me, nitrogen trihydride, because I never called it nitrogen trihydride. But it makes sense because probably not everybody calls it ammonia. And so I was able to order some nitrogen trihydride. You have to have some flexibility there, but when it comes to the test, then stick with a set of rules and then follow that. All right, other questions on this? No? So last time we were looking at this particular problem, the tetramine complex of copper 2, or tetramine copper 2 ion. The formation of this. And we're looking at the Kc for this. Kc is 1.1 times 10 to the 13. It's a highly favorable reaction. And so I asked you to fill out the ice table. So tell me what you got for the ice table. So initially we had 0.100 molar, okay, and then 6.0 molar. 6.00 molar, and then 0 molar. And so somebody tell me what they got for the change. Minus X. Okay, I usually do minus X molar, just to make sure it's all right. And then minus 4X, and then plus X. Good. All right, for the equilibrium line, what did you get? Yeah, 100 minus X. Keep track of the sig figs. X molar. All right, and then setting up the Kc equation, we should write out here. Okay, we aren't going to put the X's in yet. We're going to put in the concentration of the products. What happens is now I have double square brackets. A lot of people, including me, don't really like to write double square brackets. And so what I tend to do is get rid of one set of square brackets. And so this would be the concentration of the complex. But what I'll probably end up doing is getting rid of this set of square brackets, so let's say the concentration of this complex. molar concentration. Just to keep it easier, but for right now, I'll leave it in there. What do we do with the do we square this, or? No. Okay, this is going to be divided by the copper 2+ concentration, raised to the first power, the coefficient is 1, and the ammonia concentration. A lot of people forget this, though. What do I need to do the ammonia concentration? To the 4th power. All right, then we plug these in because we now have a way to solve for x and what x is. And so the complex is x. Here I don't bother with the units. Over there, I'm going to keep track of the units. Over here, I don't. So this is going 100 minus x. And then this is going to be 6.00 minus 4x to the 4th power. Is that what everybody got? All right, now, how would you solve for x on this particular problem? Do you think the quickest method of solving for x is? Guess and check? Successive approximations? The successive approximations will work for this. For sure you'd want to do it because the algebra is too horrendous. Those 5th order equations too much. But guess and check is not the quickest way to do this problem. There's an even faster way to do this problem. And so somebody who does guess and check might take 10 minutes. Somebody who does this alternate method might take a minute. Probably takes 10 times less time. Well, what is this alternate method? And so we have 2 ways to solve this. One is just, we don't call it the guess and check method, we call it what? Method of successive approximations. Maybe guess and check just doesn't sound scientific enough. So, method of successive approximation. It's for sure that will work, but it's too time consuming. And on exams or whatever, you want to do things quickly. So what are some tricks that we can do that might help us? And would these tricks have worked on the previous problem? We'll see. These tricks don't always work. So for example, the previous problem we did, it wouldn't work necessarily there, but it'll work here. There are 2 tricks, additional tricks that you should know, in addition to the method of successive approximations. One is called reset initial conditions. And so in other words, we just reset I. And then 2 is SA. SA stands for simplifying assumption. Assumption. These 2 methods are going to make this problem much simpler than guess and check, for sure. And this is perfect for this because when I look at K tells me something. K says that this is heavily biased towards product or towards reactant. Yeah, this is heavily biased towards product. And so the reset the initial conditions involves something like this. If we think about something that's heavily biased, I can make a water tank like this. And fill it with water. If I fill this water tank with water, do I get much water on the left side compared to the right side? If I fill it, the water levels are going to be equal, right? Two water levels have to be equal. But the amount of water on each side is totally unequal. This is like a dynamic equilibrium. Can water flow back and forth? Yeah, but there's no net change in level or amounts. So dynamic equilibrium. one side, I'm gonna call the left side the reactant side, the right side is gonna be the product side. So do you see this is heavily biased towards product, right? And then I'm gonna put in 100 gallons of water here. So I have 100 gallons of water. Shouldn't have used blue. Okay. So reset is like this, you know, right now, when I visualize this, you know, this is what it should be, you know, the water or the atoms. We think of the water as being atoms. And so most of the atoms should be on the right side on this. In fact, most of the water molecules should be on the right side. But when I look at this, all 100 gallons, when I look at the initial conditions, and I say I have 100 gallons of atoms, all 100 gallons of atoms are on the reactant side. And I have 0 gallons of atoms on the product side. And so what this is going to look like, you know, in my mind, is something like this. I'm going to have to make the left side quite tall for the 100 gallons worth. Here. Oops. So when I look at my original initial conditions, is like this. All the atoms are on the left. There are no atoms on the right. And so I have all 100 gallons over here. And so when I open the little door, let's say I have a door blocking the water here. When I open it, you know, how many gallons of water are going to go from left to right? Practically all of it, you know. Let's say there's 99.9999 gallons over here and only 0.01 gallon over here. So there's going to be a tremendous change because there's got to be huge flow of water, right? So water should be biased towards the right side. And so what I'm going to do here is this. Okay, when I open this, you know, when I open this, it's going to go to some equilibrium situation like this, you know, where most of the water's over here. But what I'm going to do is this. Rather than starting with all 100 gallons on the left side, I'm just going to push all the water from the left side to the right side. And so what I'll do is I'm going to start with 0 gallons on the left and 100 gallons on the right. And this is called resetting the initial conditions. And so in other words, rather than moving the water, I'm going to move all the atoms. So what I'm going to do is I'm going to just get rid of this. Get rid of this. And then we're going to try this. We're going to try to reset this. Okay, so what I'll say is I'm going to reset to the right. When I reset it to the right, I'm going to get rid of all the atoms on the left. But I run into a problem. I can't get rid of all the atoms on the left because I have a situation of limiting and excess. And so when I look at this ratio here, it's a 1:4 ratio. What's my limiting reagent here? The copper 2. And so what I'm going to do is I'm going to push this reaction all this way, but to get a new set of initials. But the new set of initials, I'm going to get rid of all my copper. If I get rid of all my copper, I'm not going to get rid of all my ammonia. I can't. And so what I use for reset is I use Y. So if I lost Y molar of copper, how much ammonia have I lost? And so I already know what Y is because this is my limiting reactant. I'm going to push all those atoms to the other side. So Y is 0.100 molar, minus 0.100 molar. And so how much of the ammonia have I lost? Minus 4Y. And that's going to give me how much remaining on the left side. Yeah, it's going to be 5.60 molar. Do you see that? Because if I lose 0.100 of this, I'm going to lose 0.400. I'm going to lose 4 times as much, right? And I can't lose more than that because I don't have any more copper to get rid of it. Over here on the product, this is going to be plus Y. And so over here on the product, I'm going to get 0.100. And so what I'm going to do is I'm going to push as many atoms as possible from the left side to the right side. Here. And so what I'll end up getting is I'll end up getting all 100 gallons of water on the right side now, rather than the left. Like this. So now when I open the door to let the water flow, is very much water going to flow from right to left? No, not that much. A little bit of water will flow to fill up this part, but it's not that much, right? And so this is what's going to happen. Now the water is going to flow in the reverse direction. So rather than getting minus, minus, plus, it's going to be plus, plus 4x molar, minus x molar. And so now I open the door. But the key here is, did I create or destroy atoms? No, I still have the exact same. So I still have 100 gallons. You know? I can't all of a sudden have 90 gallons. You know, I've got to make sure the total number of atoms is the same. So at equilibrium, I'm going to have x molar, 5.60 plus 4x molar, and then 0.100 minus x molar. And so this is called reset the initial conditions. The strategy in resetting is to reset it to the bias side, you know, depending on what K is. If K favors the product, we reset it to the product. If K favors the reactant, we reset it to the reactants. If it's backwards, you know, if you see a scenario where, you know, all the water should be on the right, but it's on the left, then that's a good candidate for resetting. And so we see, what did resetting do? And so this was the equation without resetting. The equation with resetting looks a little different now. So rather than having x up there, now we're going to have 0.100 minus x up here. And then down here we're going to have x. And this is going to be 5.60 plus 4x to the 4th. So compare these two equations. Did resetting make it simpler? Quicker to solve? Not really. Not really? Doesn't that look a lot easier to solve? Looks the same?
Yeah. Is that 5.0?
5.60. 5.60. The 5.60?
Yeah.
Because if I lose 0.100 moles of copper, I'm going to lose 0.400 moles of ammonia. And so what I'm going to do is I'm going to reset it. That is, I'm going to have complete forward reaction. Reset as many atoms as possible. And so I'm going to lose all my copper. It's going to go down to 0. And that means it's got to be 4. Y here, this is Y. And so Y is going to be 0.100, so this is 4 times 0.100, it's going to be minus 0.4. That's going to leave me with 5.6. I can't lose more ammonia. I can't reset these ammonias over here because I need to react it with copper to get the right product. You know, I can't just say, okay, I'm going to get rid of the rest of the 5.6 ammonia, but each ammonia needs to be bonded to a copper. And so I run out of copper. I can't make any more product. And so in other words, I'm assuming 100% forward reaction. Just assuming. How can you do that? Well, how you can do that is, if you have 100 gallons of water, you could either have it on the left side or the right side. Does it matter? No, as long as you keep it at 100 gallons. Now, you go, sure it matters. Because when you open the door, will the ratio, be any different. And so if we start with all the water on the left side versus all 100 gallons on the right side, on the right side. So this is 100 gallons over here, this is 100 gallons over here. Are we going to get a different endpoint, a different equilibrium, or are we going to get the same? It'll be exactly the same. And so we're going to end up at the same place. Doesn't matter. And so this is what all we're doing here. Right now, all the atoms are on the left. What we're going to do is I'm going to shift them to the right, as many as we can. But this is complicated because we have limiting reagents down here. And so we try to do this to make math simpler, but when you look at it, it looks the same. Rather than having a binomial down here, we have a binomial up here. Does it really make it simpler? Well, for me it does, because I hate multiplying. If you have this, which would be a fourth order, multiplied by binomial, you know, it's easier to just do this and raise it to the fourth power. So just multiply the binomials once, and 3 times, and 4 times, and then multiply by x. Right? So maybe a little bit simpler, maybe not. Probably I wouldn't be multiplying binomials. You know what I'd do? This looks no different. This looks like I have to use successive approximations. But I have one more trick. The last trick is to use something called the simplifying assumption. The simplifying assumption works like this. What we do is, you know, if we start with all the water on the left side, then we look at the change. You know, if we start with all the water on the left side, the change is going to be huge. In other words, we're going to have a huge flow of water from left to right, because the right side is a big tank, the left side is a tiny tank, right? And so what we say is that the change is going to be big here. And so when we start with the atoms on the left, the change is going to be big. Same thing here. If we start with all the atoms on the left and no atoms on the right, we see that K heavily favors the product. And therefore, in order to heavily favor the product, the change is going to be big, right? Versus if we start with all the water on the right side and then open the door, the change is small. The change is small because not much water is going to trickle over. Because it doesn't take much to fill to the left side. Does that make sense? Or not? And so this is how this becomes such an easy problem to solve. What we say is this. We say that the change is small. And so we don't expect to lose much. And so if all 100 gallons is on the right, you know, just very little bit is going to go to the left, 0.001 gallons, right? And so we say that, well, if I start off with 100 gallons, I'm not going to lose many. Very little is going to go to the left side. And so what I say is that 0.100 minus x is, well, we have about 100 gallons on the right side, so it's going to be 0.100. I just lose a little bit, but not significant compared to the original 100. Does that make sense? All right, and so what we do is this. 0.100 minus x is about equal to 0.100, because of the scenario that we gave earlier. You know, the actual endpoint, let's say, is something like this. You know, at equilibrium, it should be 99.9999 gallons over here, and then maybe 0.0001 gallon over here, right? So we don't lose much. Okay, that's one. Then 2 is this, you know, 5.60 plus x. Well, if we're losing that, we're not going to gain much on the left side, right? And so 5.0 plus x, you know, we're going to assume that x is very small. The change is very small. And so 5.60 plus x is going to be about equal to 5.60. And so x, the change, is very small. And then 3. 3 is 0 plus x. So, you know, when I'm looking at what happens to the copper 2 on the left side, I say 0 plus x. Can I say 0 plus x is about equal to 0? You know, I can say the change is small. So does it work in this case? 0 plus x is about equal to 0. So, you know, if I start off with 0 gallons, let's say, if I start off with 0 gallons, because I'm going with this scenario here, all 100 gallons on the right, I got 0 gallons on the left. So if I start off with 0 gallons and I gain 0.001 gallons, does that change small? It seems small, I just don't generate that much water, right? But in this case, the change is big. Why? Why is the change big in this case? The change is big in this case is because, you know, can I say that, this is the point, can I say 10 to the minus 4 is about equal to 0? You know, if I get 10 to the minus 4, that's about the same as 0. Is that valid? Or should I say maybe 10 to the minus 100? If I had 10 to the minus 100, that's about the same as 0. 10 to the minus 100, about the same as 0. You might say, no, we've got to go bigger. 10 to the minus a million. 10 to the minus a million. If I had 10 to the minus 1 million, that's 1 billion. Is that close enough to 0? Yeah? That's close enough to 0? Okay. If 10 to the minus a million is the cutoff, we're going to say 10 to the minus a million is so small it's close enough to 0, right? Let's calculate the percent change. The percent change is this. The percent change is the change over the initial times 100%. And so, you know, if I get 10 to the minus a million, I started off with 0, then that's a pretty small change, right? It'd be like saying, you know, if you started off at 0 degrees Celsius and you went up by 1/1,000,000th of a degree of Celsius, is that change significant? No. It doesn't seem significant at all, but when we do this, this is something we'll realize. Okay, so we just went up just a tiny bit, you know. Do this. 10 to the minus 10 to the 6th is our change. Our initial is 0 times 100% gives us a percent change of what? Hmm? Yeah. It's infinity, right? Is that a small change? This would be an infinite percent change, no matter how small x is. Because the only time you can say x is about equal to 0 is when x is about 10 to the minus infinity, right? That's small, that's close to 0. 10 to the minus a million is still considered big. And so any change compared to 0 is significant, because 0 is nothing. 0 is 10 to the minus infinity, right? And so we cannot do it here. It doesn't work. But the first two we can say it's small. And so what this does is with the SA, it makes the math simpler, because what we can do is we can say the 0.100 minus x is about equal to 0.100. And then x stays there because x is always significant compared to 0. And then 5.60 plus 4x is about 5.60. And so now we raise it to the 4. All right, look at the math here. Is the math here easy? The math here is so easy. This is why I say this will take 100 times less time than using successive approximations. You know, if you're doing it like this and your neighbor is using successive approximations, you'd be already on the problem number 50 and your neighbor's still working on problem number 1, right? Kind of thing. And so, but then you go, well, that's not right. You know, this is not accurate. You're right, it isn't accurate. But as long as the answer comes out close, then we're happy. So let's see, you know, if the answer comes out close, and then we have to justify this as well. And so let's calculate what x is here. And so x is a simple calculation because x is just equal to 0.100 divided by 1.1 times 10 to the 13 divided by 5.6 to raise to the 4th power. And x comes out to yeah, punch it out on your calculator. Verify this one. Does that look okay for the number? No? What do you get?
Yeah, I'm gonna be, 1.08 times 10 to the 17th power.
Positive 17? Oh, there must be an error. If we solve for x, we'll multiply both sides by x and divide by 1.1 times 10 to the 13. And so punch this into your calculator. 0.1 divided by 1.1 times 10 to the 13 divided by 5.6 half to the 4.
Times 10? No, divided by?
5.6 hat 4, or you know, whatever, exponent 4. It depends on your calculator. Times 10 to the negative 18. Okay. Yeah, you want to make sure. And so this is our x value. But, you know, we did this. We just ignored these, right? And so this isn't the right answer, right? But as long as it's close enough, then we're okay. And so what we're going to do is we'll just figure it out. Well, the change relative to 0, can I just call this 0? No, because 0 is nothing. And so here at equilibrium, I'm going to have 9.24 times 10 to the minus 18 molar. 10 to the minus 18 molar is nowhere near 0, right? But 0 is 10 to the minus infinity. And so this is significant here. Then we're going to calculate the next concentration. It's going to be 5.60 plus 4 times that. Now 4 times that is going to be 4 times 9 is 36, and 4 times 24 is 96. So this is 36.96 times 10 to the minus 18. So 36 times, so I'm going to need 16 zeros. And so I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14, 15, 16. Actually, I need 17 zeros. 3, 36, 96. All right? That would be it. And so if I do 5.60 plus this, I'm gonna get 5.60, and then these are extras, so I'll subscript those. 1, 3, 6, 9, 12, 15 zeros. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 3, 6, 9, 6 more. So here, was the change significant here? No. I mean, I barely added any, so just a trickle of water went back to the other side. Here, that trickle is significant though, here, right? I can't call this 0 because compared to 0, someone went here. Okay, and then the final calculation here is 0.100 minus x. Well, x is that, so I'll need 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 924. So, calculate this. This is going to be 0.099999999999924. If I got the correct number of 9. Did we lose much here? If you were to plug this number in your calculator, try it, and then hit enter, and tell me what you get. 0.1, because your calculator is going to round this, right? 0.1. And so, yeah, it's pretty much 0.1. In fact, you aren't going to be able to punch that into your calculator. And so we'll just call it 0.1. Now, we did something. We screwed up the equation, right? So if we screw up the equation like that, is this answer very accurate? Well, one way to test the accuracy of our answer is by doing the double check. So we're going to double check this by plugging these equilibrium concentrations back into Kc and seeing does it equal 1.1 times 10 to the 13. And so we're going to calculate K. And so we calculate K. Probably the easiest is, because the calculator can't carry that many digits, just type in 0.1 for this, divided by 9.28 times 10 to the minus 18 for this, divided by 5.6, and your calculator's not going to carry those, just 5.6 raised to the 4th power. And then what does K come out to?
It's 1.9 times 10 to the 15.
1.9 times 10 to the 15.
Mm-hmm.
1.9 times 10 to the 15. It's supposed to be 1.1 times 10 to the 13. Is that close? No, it's way off. Could we attribute being way off to round off error? Because we did round it. No. You got 1.1? And so what happens is this answer is way off. So we double check the calculation. Double check, it comes out to 1.10, right? 00 times 10 to the 13, which checks. That's supposed to. And so even though we made that simplifying assumption, which you go, you know, that's not right, and mathematically it's not right, but the answer is so close that the K came right on. Now, in general, what we're going to do is this. Before we calculate the equilibrium states, we always justify our assumption. And so here, this is one way to justify, but typically you don't want to go through this calculation because doing this calculation for the equilibrium is a hassle if the assumption is not justified. So, you know, typically I would insert a step here. After calculating x using SA, we need to justify it. And when we justify it, it's a little bit of a circular justification because we're using the wrong answer, that is our assumed, you know, answer for the justification itself. And so what we do is we calculate the percent change. If the percent change is less than 5%, which is a total arbitrary cutoff, then we say it's okay to use. And so this is, obviously the smaller the percent change, the better, because if you look at the percent change, was the percent change significant here? No, insignificant. Was the percent change significant? No. Here, was the percent change significant? Yes. Here, but that's because it's 0. And so when we calculate the percent change, we calculate it like this. The percent change is just equal to the change. Oh, actually, I have it written over there. And so we need to calculate it for the ammonia first. Let's go ahead and do it. For the ammonia, the percent change is the change, that is 2x, over the initial, which is 5.60 times 100%. So what is 2x? 2x is 36.96. I think, or was it 90? Yeah, 3690.96 times 10 to the minus 18, divided by 5.6 times 100. What does that come out to? Yeah, 10 to the negative 18% is negative 16. 10 to the negative 16% change is exceedingly small. So the smaller the percent change, the better this works. And so this should work pretty well, which it did. And let's look at the percent change for the complex. The percent change for the complex is x over 0.100 times 100%. And so the percent change for the complex is going to be x, which we got earlier, 9 point. So it's going to be 9.24 times 10 to the, this minus 18, so it's going to be minus 17, minus 16, minus 15, 10 to the minus 15%. And so it's okay there. And so the percent change is very small, so the simplifying assumption should work pretty well.
How do you get 2x from ammonia?
Oh, I'm sorry, it's not 2x, it's 4x. 4x is going to change it. But it's 36, well, it doesn't change this number. This is 4x, 36.98 times 10 to the minus 18. So it's 36.98 times 10 to the minus 18 divided by 5.6 times 100. And what does that come out to? 6.6 times 10 to the negative 16. Still very small. All right, and so if we have the strategy that we're going to reset this and then do the calculation, this calculation is very quick. The math is very easy, right? Compared to successive approximations. Successive approximations, you're going to be punching in lots of numbers, and it takes a while. Unfortunately, this doesn't work for everything. So let's look at another scenario. So this next example we're going to look at is the copper 2 plus, 2B plus the tin 2 plus, and yields 2 copper 2 pluses plus a tin 4 plus. And so we're going to revisit this original equilibrium. Well, when I look at KC is 1.48. If K is 1.48, and let's say I have 100 gallons of water, if I have 100 gallons of water, is it mostly on the right side of this, or is it mostly on the left side, or neither one of those? You look at the K value, how's the water distributed? Well, K is close to 1, which means it's a 1-to-1, close to a 1-to-1 ratio. If it's close to 1-to-1 ratio, I expect about 50 gallons on the left and about 50 gallons on the right, except it's a little greater than 1. You know, it's 1.48, so it's 1.48 to 1. So maybe a little more, right? 75 gallons and 25 gallons, something like that, right? That's kind of what you expect, correct? A little bit biased, but about 1-to-1. And so in this case, you know, one of the strategies is resetting that. When we reset it, we're going to screw it up because it's kind of, well, we might, it depends. Because if we reset it to one side or the other, well, this is more 50-50. And so let's take a look at this scenario where I have 0.100 molar, 0.300 molar, 0.200 molar, and 0.200 molar. And so right now I have kind of a 50-50 mix, right, of atoms, sort of. Do you see that? It's like a 50-50 mix. And so it looks like it's close to where it should be, which is good. It's close to where it should be. And so the first thing is, if it's close to where it should be, then maybe I'm not going to reset this, because if I reset it all to the right, then I'm going to have a huge rush to the left. Or if I reset it to the left, I'm going to have a huge rush. In other words, the change should be big, right? And so we'll just leave this as is. What do you think about that? But the thing we have to figure out is it going to flow to the right or is it going to flow to the left? Can you look at it and tell me which way? Maybe it looks kind of like it should flow to the right because, you know, it's a little bit bigger than 1, you know, 1-to-1 or something like that. And so it kind of looks like it should be a minus 2x molar, minus x molar, plus 2x molar, plus x molar type scenario, right? Doesn't it look like that? But it's tricky. Why is it tricky? It's tricky because of the, you know, concentrations here, and then also the squared terms. And so, you know, it might actually not be this. It might actually flow to the left. That is, it might actually go, you know, so I'm going to write, or it could be plus 2x molar, plus x molar, minus 2x molar, minus x molar. You know, actually I don't really know because, you know, it just kind of looks like it's going to go to the right, but I'm not 100% sure. And so what should I do in this scenario? Well, if I'm ever uncertain, then the way we figure out which way it will flow or which direction it will shift is by doing a Q calc. Q is called the reaction quotient.